Okay, welcome back everybody. In this video, we're gonna look over a new topic. We're gonna talk about heat integration. So in a chemical plant, in a continuous chemical plant, you have various streams that need to be heated up. For example, the feed entering a reactor, it needs to be heated up to a high temperature. And you have various streams that need to be cooled down. So you need to perform heating tasks and you need to perform cooling tasks. So some of the ways you can heat up your streams before they enter a reactor is use fired heaters. You can use steam at different pressures depending on the required temperatures. Whereas for cooling requirements, if you have a very hot reactor effluent, you want to cool it down to maybe condense some of the vapor and perform separation. You can use cooling water as the cooling utility. You can use air. In order to make the process more economical, what if we could use some heat from our hot streams? And so we need to perform some heating tasks, whereas the other streams need to be cooled down. What if we were able to take heat from the hot streams and give that to the cold streams, thereby minimizing our reliance on utilities? Utilities are one of the most expensive operating costs in a chemical plant, and by performing heat integration, you can cut back on utility costs and make your chemical plant much more economical. So we're gonna to get a better idea of like the systematic procedure through which heat integration is performed. We're gonna look at a very simple scenario where we only have two streams. And this is the kind of problem that you'll probably see on an exam. Okay, here we have a very simple problem laid out here. We have a cold stream that needs to be heated up from a source temperature of 100 to a target temperature of 530. We have the mass flow rates and we have the heat capacity. Similarly, we have a hot stream that needs to be cooled down from 530 Fahrenheit to 100 Fahrenheit. The mass flow rate and heat capacity are given. Now the enthalpy change associated with this heating task is going to be, we can calculate that by just applying the equation for the change in enthalpy, T target minus T source. We have our flow rate, we have our heat capacity, and we know our temperatures. Our flow rate was 10,000, heat capacity 1 BTU per pound mass, and a temperature change of 530 minus 100. So that comes out to be a total energy enthalpy change of 4,300,000 BTU per hour. So this is the energy that needs to be added. Now for the second task, we're cooling down the stream from 530 Fahrenheit to 100 Fahrenheit. So for this stream, your delta H is going to be negative, meaning heat must be taken away from this stream. So 20,000 are mass flow rate times the heat capacity 0.6 times the delta H. Negative 5,160,000 BTU per hour. Okay, so if you perform a first law analysis, you can see that the energy required by the cold stream is not equal to the energy given off energy given off by the hot stream. So in the end, you'll have to provide, if you add these up, you'll be left with a deficit of 5160 negative 860,000 BTU per hour. That's the energy that you'll have to that's the cooling duty that you'll have to provide in order to like the total cooling duty that you'll have to provide to in order to like successfully meet the tasks. But that's just the first law analysis. Now the second law states that the second law will tell you that in order to transfer heat, you need to have a change in temperature, and heat obviously flows from a higher temperature to a lower temperature. Okay, so in order to like better visualize how we're gonna tackle this problem, I have my temperature enthalpy graph here. Let me start this from the beginning so that like we're all up to pace. So I have my temperature on the x-axis, the temperature on the y-axis. I have my enthalpy on the x-axis. Now the enthalpy of a stream will be equal to mCp times the temperature minus a reference temperature. Now if I'm able to rearrange this to have temperature as the subject of this equation, I'll get over mCp plus Tref. So you'll see that the slope of the equation is going to be 1 over mCp. So the higher the mass flow rate, the higher the heat capacity times the mass flow rate, the smaller the slope is going to be. And always you're going to have the hot stream on top and the cold stream below the hot stream, because you're going to be transferring heat from higher temperature to a lower temperature. So our hot stream goes from 530 all the way down to 100, starting off at 530 and goes down to 530. Okay, before I draw the cold stream, one of the most important variables in heat integration and heat exchange network design is the minimum approach temperature. In order to explain what that is, so for a heat exchanger, for a countercurrent heat exchanger, you have two streams running countercurrent, and both of these streams, there's a hot side and there's a cold side. So there's a temperature difference between both of the streams, and that temperature dictates the driving force of the heat transfer, and it's going to impact the size of the heat exchanger. Now the bigger the driving force, the smaller the heat exchanger is going to be, and so that impacts the area of the heat exchanger, but as you can see, it has other impacts on how much utility you're going to use. So we're going to pick a delta T minimum of, let's say, 10 Fahrenheit in our case. And again, this is it's up to you. Anywhere between 5 to 25 is a reasonable first estimate for a base design. Once you have a base design, we're always going to optimize. Okay, so we have our hot stream. Now for our cold stream, our mCp is going to be, for our cold stream, the mass flow rate times Cp is going to be 10,000 times 1, whereas for hot stream, our mass flow rate times Cp was 20,000 times 0.6. And you can see that for the hot stream, the mCp is higher, which means that the slope of the line, remember that slope is equal to 1 over mCp. So the slope for the cold stream is going to be 1 over 10,000, and the slope for the hot stream is going to be 1 over, this comes out to be 12,000, I believe. Let me check. Yep. So the cold stream actually has the bigger slope. What that means is, on the temperature enthalpy diagram, your cold stream curve is going to be steeper, and you can see it still has to go from 100 to 530. That depends on our source and target temperature. And notice how the temperature difference on one side, on the cold side, and the temperature difference on the hot side are different. In our case, since the slope of our cold stream was bigger than the slope of our hot stream, if that's the scenario, your minimum approach temperature is going to exist at the hot side. If it was the other way around, let's suppose your cold stream had a smaller slope and looked something like this, then the minimum approach temperature is occurring on the cold side of the heat exchanger. So just a point to be wary when you're solving problem. So once again, our minimum approach temperature, we've already set that to be 10 degrees Fahrenheit. So our minimum approach temperature is going to occur here. 10 minus 530, that's going to be 520. So the temperature here is going to be 520. And we know that our cold stream must meet the target of 530. And it's going to come down to 100. Okay, so this is not drawn to scale. Right now, this shaded region that I'm going to show you is going to be the area of heat exchange. So yellow represents the area where we can exchange heat. The blue region is going to represent the cooling requirement, because we still have to heat this stream down from this intermediate temperature all the way to 100. And red on the other side is going to represent the heating requirement, because we still need to heat up this cold stream from 520 all the way to 530, and we're not exchanging heat within that zone. Now let's say if we had a different minimum approach temperature, let's say we had a minimum approach temperature of 5, and how would that impact our heat exchange network? So if I just get rid of that, get rid of these intermediate temperatures, now my minimum approach temperature, once again the pinch, which is the where the minimum approach temperature occurs, it's going to be on the hot side. So 525. 525. Now, as you can see, the region over which you're exchanging heat, as you lower the minimum approach temperature, the region over which you're exchanging heat becomes smaller. But now your heat exchangers are going to be bigger because of the smaller temperature difference. Smaller delta T's, smaller driving force leading to bigger heat exchangers. Now that's what I meant by when I said that the minimum approach temperature, choosing the right minimum approach temperature is going to be an optimization problem. So let's just continue these calculations with 5 Fahrenheit. So in order to calculate the size of our heat exchanger, we know these two temperatures, the hot side, and we don't know this cold side yet. So the intermediate temperature of my hot stream. And I can do that I can find that by performing a simple energy balance. Let's say on the top I'll have my hot stream going at a flow rate of 20,000 pounds per hour, CP 0.6, and my hot stream is entering at 530, and hot stream exits at a temperature that we don't know yet. TH intermediate, that's what I'm calling it. The cold stream enters at a flow rate of 10,000, heat capacity 1. Temperature, and we found that by the temperature at which the stream enters is going to be 100. That's the source temperature. And the temperature at which it leaves is going to be the temperature of the source temperature of the hot stream minus the minimum approach temperature, which in our case is 525. Okay, so in order to find this minimum approach temperature, you can perform a energy balance. Q equals MCP for the cold side equals MCP for the hot side. And the outlet temperature comes out to be 175.83 Fahrenheit. So this temperature right here is equal to 175.83 Fahrenheit. Okay, so we know the temperatures of all streams, and once we know each stream's temperature, we can use the design equation to find the area of the heat exchanger. Now there's gonna be yellow represents the so in the yellow region you're gonna have the area of the heat exchanger, but for the cooling region and the heating region, you're still gonna need a heater and a cooler that either uses steam for heating or a hot oil, depending on the temperatures you're operating at. And those heaters and coolers are also will need to be sized. So in practice, this is what your network is going to look like. So you have your heat exchanger, and in our case we had the hot stream entering the heat exchanger and we had the cold stream entering the heat exchanger at the source temperature. Now once the hot stream leaves, it has to pass through a cooler to meet its target temperature. And once the cold stream leaves the exchanger, it has to pass through a heater to meet its target temperature. Let me color code that. And keep in mind that we're not dealing with phase changes right now. Once phase changes become involved, the heat exchange network design becomes more complicated. And once you know the once you know the heat transfer coefficients for the heat exchanger and the heat transfer coefficient associated with the heater and cooler, you can determine the sizes of your heat exchanger by using the design equation. And that pretty much sums up. Just a closing remark: the impact of minimum temperature. As the minimum approach temperature increases, your heat exchanger area, the area of this heat exchanger, is gonna go down, but your utility usage is gonna go up, and vice versa. So that's the trade-off when you're selecting the minimum approach temperature, and you need an objective function that deals with the cost from using which you can perform an optimization. So in the next video, we're gonna look at scenarios where you have more than two streams, where you have like multiple hot streams and multiple cold streams, and how we can perform heat integration with more complicated tasks.